Welcome to MorpheusChair, the program where you learn how to build robots like these from your comfy chairs. So this is the end of this Build Your Line Following Robot series with Raspberry Pi. So if you liked it, please consider hitting that like button and subscribing, because that helps us a lot to know if you like this type of content and if we have to continue doing it and doing more awesome stuff like this. Please leave in the comments which projects you would like us to build, to do, because we have some options, but we would like to give you voice to you audience that you have supported us so well. So we would love to know your opinions and your ideas and make those ideas true. Yeah, so let's go to this video. So this last video we will talk about two things. Basically all the code differences and modifications that we had to do in order to make the transition from the simulated robot, idyllic simulated robot, to this real slow and clunky robot. So all the different changes that we had to do to make this work. This is one part. And the other one is a little show off of the build that we did for this. As you can see, we added a stand and we added like a dodgy 9-volt battery, because I'll explain for the reasons for that. But basically we'll see that and a demonstration on how this works. Yeah? Okay. So, yeah. I think that's it. Wait. Oh. They are telling me, my imaginary friends and colleagues, that we have a special guest today. Okay. So we have a special guest here. This is a robot inspired by the Sony Curio robot. If you don't know what it is, you're dead inside, I don't know. Please have a look at it. The videos, type Curio Sony. It's a fantastic robot, my favorite robot. And yeah, and come back again. And this is a robot inspired for that I built years and years ago. Yeah, so I think, well, we have a special message here. Let me, wait a second. To the workbench. To the workbench. Sorry. To the workbench. To the workbench. Hi and welcome to this explanation on the code to make the change from the simulated robot to the real robot. So what we had to change, what do we have to change to make the transition between this simulated robot to the real robot? Well, actually quite a lot of things, and we're going to talk about the three main aspects that we had to change. So let's go. So the first thing is the color calibration. So the color calibration means that if we go to the simulation, you can see that the color, the line is totally white. So it should be 255 in RGB. Okay. In reality, you won't have a perfectly white line. This means that when you go to the place, you'll have to calibrate it. So for that, what I did was make a tiny photograph. You do a screen capture of the camera feed, and you save that image, and then you go to your favorite color picker. I have this one, which is an extension of Chrome, And then what I do is I go here and I get the color. So I see that more or less it's around 148, 45 in the R, and it oscillates around those values. So basically I pick one, and based on that, I put that in the launch file for the line follower. So as you can see in the line follower, we have several arguments. One of them is the RGB. So we place here the basic color that we want to follow. And this, you'll probably have to do it every time you change of place, because the white, it will change slightly in some places and a lot in others. It depends on the ambient light, it depends on light noise that you may have, so a lot of things. So you have to calibrate it each time that you go in the place, and each time you do it more or less, because you can calibrate in the same room, in the same place, but because it changes the time of the day, the light is different. So bear that in mind. Then one of the things I've seen that works best is also not being that restrictive with the color error. So I think that 20% is a good number, because it catches more or less all the colors, all the varieties of the same color that you want to track. And at the end we have the mode. So this is you can put color calibration basically, or any other name. If you put any other name, then it will start the following line. And the basic difference on that is if we go to line follower, by the way, I've done two, like I've done the simulated version and the real robot version, because it has quite a lot of changes actually. Returning to the calibration color, so the color calibration, so we have essentially what it does is it shows the original image, or it shows the resulting image, or after the detection and the centroid and the blob detection, all that stuff. If you're in the color calibration, you'll see this, and you'll use that to save the calibrated image. Yeah. Okay. This is talking about the color calibration. So these are the modifications that we have done so that it works on reality. We have to talk about other 2 points. The first one is the image latency, and so on. So in simulation, you have very good latency, but in reality, you have a system that it's slow, and making all these calculations takes time. And this means that it has a very serious impact in performance, because if we go to the simulation, we can see that when the robot detects the line, immediately it will move the wheels to counteract that, okay, and move accordingly. In reality, it's much slower, and you have issues related to performance and all that stuff. So we have to make optimizations so that it goes as fast as we can. That's why I made 2 versions. In this one, we don't do we get, for example, if we go here, we see that the centers, we don't iterate to see all the centers that there are and all that stuff. It just, we just don't do it. We just get the first one that we can detect, and that's it. This, it should have an impact in performance. Also, remove all the prints in all your Pythons, not only in the line follower, but in everything else. And that's all for performance. And the most important thing is that we are dropping frames. I generated this drop frames variable, and here what we state is how many frames do we drop until we process a new image. And this is like an equilibrium, because if you drop too many, then you lose a lot of information. If you drop too few, then you'll impact in performance, because it's trying to process that all the time. So it's experimentally see what it works best for your system. That's for working in the latency and performance. And finally, and this is the most critical part, is the fact that even if you had the perfect system of image that we don't have, so there's a delay between what we see in reality and what we get in the images. This means that there's a delay. So this impacts in performance and in the way the robot moves. Because you might think that the line is, I don't know, you say, hey, I'm here, right? But in reality, you're not seeing this. You may be seeing this. This means that you'll make a decision based on something that is old. So that affects a lot. But the other thing is that even if you have this image latency fixed, then you have a latency in the commands and the movements of the robot. They are not as precise as in the simulation. In the simulation, they are really precise. In reality, you have battery issues. Depending on the batteries that you use, it will go slower, and some speeds won't work, this kind of stuff. So at the end, what I did was modify the way we send the commands and the way we turn. So let's go first to what are we sending exactly? So if we go to line and we go to the move robots, so what you have to see is that we are simplifying the way it turns the robot. So you can see that we are checking, for example, let me just talk about this first. So here we're saying, okay, if linear is positive, then we give it a certain value. We don't change it. We never change it. If it's negative, then the same value, negative. And if it's 0, 0. We don't graduate based on the distance. We don't do all that stuff that in simulation we did. And the reason is because in the real robots, there are certain values that don't work and certain values that are too fast. So what I decided is just give it very stable speeds, very slow speeds, and that way it won't go crazy. Yeah, that's one for the linear, and we do the same for the angular. And the other thing that we did also is that because there's a latency, sometimes the robot turns too much and it just goes like that. Let me show you in simulation. You say, hey, I'm a bit slightly to the left, and then I have to turn to the right, and it goes like that. Whoa. And then it loses completely the line. So what I did was a small variable that stores what was the turn that you did before. And before you lost. And when you get lost, which is this, which is when you don't see any center, any line, then it remembers that and gives you a searching pattern based on that, based on what you did before. So that allows you to, instead of turning to the right and then doing stupid stuff, if you were turning to the right before and you just lost it, in the search pattern you'll go to the left, and if you were turning to the left and you lose it, the searching pattern will be to the right. So this helps a lot in don't losing the line that fast. Okay, so we have what's all related to the line following. I know it's a lot of speaking, but it's a lot of information, and I hope you learn something of this that I had to learn the hard way. Okay, and then we go to the motor driver, and in the motor driver we're also simplifying things. So in the set wheel movement that we did in the last episode, what I've implemented is a variable that it's called simple mode. And simple mode, what it does is that we don't turn using the differential drive. If we are turning, so if both are positive, and that would be go forward, so turning to the left or to the right, but slightly, not pivoting, then what we're doing is seeing which wheel has the biggest value, and then we only activate that wheel. That way we are turning in the right direction, but we are not moving both wheels at the same time. One of the wheels will be just static, it won't move. And that gives the illusion that it's using a differential drive, but it's a more robust way of doing it for systems that are like this, very simple. So good trick, this one. And yeah, that's quite it. I made some other launches which are not relevant really. They are more tests than anything else. This one, for example, is a test to see the latency of the images, so see how it affects all this stuff. So it's good to see if your system doesn't work. And that's it. So now the only thing that we have to do is fire up the real robot and see what happens. Okay, so this will be a quick show of all the modifications I did to prepare it for the line following. So the first thing is the obvious, which is, what's this? What's this? So making tests, I saw that the batteries that we used, the AA batteries that we used, they didn't give enough power, and this made it turned me crazy sometimes, because I thought that the code was wrong, but in reality they were the batteries that they weren't giving enough juice to both motors at the same time, and that really turned me crazy. So I highly recommend you that instead of this array of I think it was 4 AA batteries, use one of these, and it works perfectly. It has higher voltage, and I've been testing for days, and it didn't run out. So fantastic. I really highly recommend you to do the setup and update it with these batteries. And then the next one is, there you go, the camera stand. So this one is a bit more serious, fortunately. So let me show you. There you go. Let me focus a bit. There you go. So what I've done is I've bought this this frame in. You can buy it in Amazon. It's for this camera, and what I've done is mounted the other way around, so that this part that is a bit thicker, I have space for Velcro. So I bought this this industrial Velcro, which is really hard, and once you put it, it won't get off unless you apply a lot of force. So it works perfectly. And then we have the stand here, which is, well, it makes the job, but of course it's not the best way. And it's from a servo, so you can see that I've just bolted one here. So it works if you bolt it correctly, and I think it serves the purpose. But of course, it would be better to put at least 2 screws to secure this. And yeah, I think that's it for the setup. What? So that's all for today. Thanks a lot for the support and to see the video until this moment. So thanks a lot. We're going to post a poll, a YouTube poll, to see what topics you would like us to address and projects to do. So please consider filling it up, because it helps a lot, basically to give you the best material we can. Until then, keep building. Keep building. Keep building. Keep building. Keep building. Subscribe. Alright.